Now, since we're studying statics, here's a key assumption that we'll make in all of the problems we'll solve today, and that is that whatever diagram or picture we're looking at, we're going to assume that it is stationary and unmoving. What we're looking at here is not then a snapshot of some situation in motion. This is what you would see if you're also watching a video of the situation. So this is all stationary. This weight is hanging off of these two cables, and the tensiometers here and here are not moving because the tension in this cable and this cable are fixed. And so when we look at this situation over here and we examine the forces acting on the system here, most useful would be to look at the forces acting on this object right here. When we add all of the forces acting upon this object right here as vectors, the resultant of those vectors should be 0. And this is one example in which we can make that assumption. Here we have a sign with a mass of 5 kilograms suspended by two cables with at an angle of 100 degrees between them. And so given that this angle over here is 180 degrees, that means that this angle over here would be 40. This angle here is also at 40 degrees. Now, because these cables are at equal angles, and let's make the assumption here that this sign is free floating on these cables. If those two assumptions are correct, then the tension on each of these cables will be the same. And so, if we were to draw a free body diagram of this situation, let's draw a diagram, the diagram of the forces acting on this attachment point, right at the joining of those two cables right here. And so, if we're going to do that, we'd have the object right here. We'd have the force that was due to the weight of the sign, we'll call that Fs, acting downward. And this is mass times the acceleration due to gravity of the sign, and this would be equal to 5 kilograms times 9.8 meters per second squared. That would equal 49 newtons. Now, in addition to that one force acting downward, there'd be this force and this force. Those should look symmetrical, even if they don't. And those are acting at an angle of, again, 40 degrees to the horizontal. Now, because we made a couple of assumptions, one that the sign is able to slide along the cables freely, thus equalizing the tension between them. If that's the case, then these tensions are equal, and because those are mirror images of each other, if the tensions are equal, that also means the horizontal components, I'll draw them in green, the horizontal components of those two tensions are also going to be equal, which makes sense because this system is neither accelerating to the left or right, so the horizontal components should be equal. And here's the other thing we can say about this situation. Those two tension forces, let's call them Ft1 and Ft2, Ft1, this is Ft2. Those two tension forces will have vertical components, and those vertical components will also be equal to each other. The other thing you can say about the vertical components is that these two upward forces, Ft1y, let's say, 1y, and Ft2y, those two vertical components will equal the one downward force of Fs. So let's write that down. In the horizontal, we can say that Ft1x is equal to, in magnitude, Ft2x. Those are over here. I'll write their names in as well. This is Ft1x. This here is Ft2x. So in the horizontal, those two forces, force components rather, are going to be equal, Ft1x and Ft2x. And in the vertical, we can say that, since again we're in equilibrium, that the two up forces must equal the one down force, which is to say that Ft1y plus Ft2y are equal to Fs. The two together are equal to Fs. Since these two are equal to each other, what we can say also is that 2 Ft(y) is equal to Fs. The y component of either of those tension forces times 2 is equal to Fs. Now since, let's move up here, since Fs we previously saw equals 49 newtons, we can say that 2 Fty equals 49 newtons, and Fty then equals 49 newtons divided by 2, and so Fty is equal to 24.5 newtons, and that will be in the up direction.